you ever found yourself looking for a product, but not quite knowing what you want? In my experience, this can often be quite frustrating because many search engines almost seem to function like database queries, where you have to know what you want and you have to be quite specific. But what if you could search using natural language? A much more natural way, much more consumer-friendly way to find products and to find search results. Today I want to show a way to do this using the Thinkwise Software Factory by utilizing the new large language model connectors, specifically the embedding, in order to do natural language processing. So here we have our search screen. At the top we've got a search bar, below that we've got a couple of filters we can use, and at the bottom we have our search results. Let's use it. Let's start by describing our perfect cup of coffee. Today I'm feeling wintry. It's getting colder in the Netherlands. Let's type in rich and velvety. I want something comforting. So we're going to search. We're going to find at the top an exotic roast described as rich and velvety. Below that, an exquisite roast. Indulge in rich and bold flavors. So we can quickly find cups of coffee, or coffee beans in this case, that really fit what we are looking for. This is incredibly useful because I didn't have to specify all sorts of filters. I didn't have to almost write a database query. I could just describe what I was looking for. So this is what we are making today. Let's look at how this actually works behind the scenes. Before we dive into the software factory, I quickly want to create a little bit of context by describing the technology we're using. So our search screen is heavily using embeddings generated by large language models. What are these embeddings and how can we use them? Let's start at the beginning with a product description. This is a small piece of text that perfectly describes our product. This is either filled in by a user or generated, depending on how you structure your data. We can then take this description, so this piece of flat text, and feed it to a large language model. This large language model will then give us back a vector embedding. This is a mathematical vector, and you can think of this as a mathematical fingerprint of the text. It is a mathematical way of describing the product. We can do the same thing with our search term. We can also generate an embedding for it and have a mathematical representation of it. That is incredibly useful because that means we have two mathematical representations, two digital fingerprints of pieces of text. We can calculate the difference between these two vectors, and this tells us something about how closely these are related. The higher the number, the closer these two vectors are related according to the large language model. This is incredibly useful because we can use this number, this difference number, as the sort order for our search screen. Because, let's face it, the higher the number, the closer the vectors are related, therefore, the more likely these are to be the products you're looking for. This is the technology we're using today. Now let's look at how we are actually implementing this in the software factory. So we are now in the software factory. In order to use these new technologies, you will obviously need a modern version of the software factory. To be specific, version 2023.3 or higher. Also, you will need an OpenAI account. You will need to provide your own API key. Once you have an API key, you can go to Model Overview, select the model you're working on, then go to Branches. In Branches, you can go to the tab Generative AI Providers, and you can add your API key here. What this does is it stores your AI key in a single place, and we can then use it all throughout our Thinkwise application. After adding our AI provider, the last thing we need to do is download the Compare Embedding solution from the ThinkStore. So we can open the ThinkStore and then start searching for Compare. And we will find the Compare Embedding solution. This solution will give you a function in which you can input two vectors, and it will return how closely related these vectors are to each other. Again, the closer to one, the closer the vectors are related. So you can install this and assign it to your model, and we can use it. Let's take a look at the data model for this solution. So at the base of everything is the product table. This table contains all of our products and its associated properties. So we see a name, we see a description, we see a purchase price, weighting grams, etc. Also, we store a product vector embedding here. This is the vector that is associated with the product. So our first half of the equation. The second half of our equation is the filter product table. This table stores the search term for each user. So we get one record per user with their current search term and, again, the associated vector embedding. We then have a view that combines the data. So we have, again, our user, we have the product ID, but we now have a search term cosine similarity. And this is how closely related these two vectors are to each other. So here we are using the function we just downloaded from the ThinkStore to determine for each product and each user how closely related the product vector is to their search term vector. So let's take a deeper look at the code behind the view. So I've got it open here in Azure Data Studio. We start with the product. This makes sense because we're trying to show products in our search results. We then join the filter product table. This is the table that stores the search terms for each user. This table has as part of its key the user ID, and we only want the results for the logged in user. So we are filtering on dbo.tsf user to make sure that the view is only returning the vector embedding similarity for the logged in user. After that, we need to generate the embedding result. We're doing this by cross-apply. So we've got cross-apply, and in that cross-apply, we are using the compare embedding function. This is the function we downloaded from the ThinkStore. This takes two inputs, two vectors. It will then return a value between 0 and 1. Again, the closer to 1, the better. So we are providing it with our product vector embedding and our search term vector embedding. And this will give us how close the search term is to the product. Again, by filtering on the user, we know how close every product is to the search term of the user. This is how the view functions and how we can get the search results. Now we have all the logic associated with the product. Let's take a look again at the screen, because this screen also has some logic on it. So this is a search product screen. What we have at the top is a form with the filter product table. We need to make sure that every single user has a record associated with itself, otherwise it can't search. Now to do this, we're again going to have a process flow, which is the create product filter record. What this does is that every single time a user opens the document filter product, we are checking whether it has a record or not in the filter product table. So again, we're doing this with process logic. So I'm going to go to code overview, and you can see that we are doing a select on the dbo.tsf user. We're checking whether it already has a filter product or not. If it does, nothing happens. But if it doesn't, it's going to create that record in the filter product table to make sure that every single time a user types something in here, there is a record associated with it. Otherwise, we'd run the risk of users not being able to type anything into this field and it becoming a mess. Now, the last thing we need to do is that we need to add the logic for our search button. So here we have our search button. This is basically just a dummy task. The only thing it does is that it triggers a process flow. So let's take a look at that process flow. So I'm going to go back to my software factory and I'm going to open it. In this case, it is filter product execute search. I'm going to go to design. And here we can see that it is quite a simple process flow. So we've got basically three actions. We've got the start table task, which is our dummy task. This is the starting point of the process flow. This is what kicks everything off. We then take our search term and we provide it to our large language model. That large language model will then return our vector embedding for the search term, and we store this, similar to what we did with product. The last thing we then need to do is refresh the table, the view, that shows us our product results. When we refresh this table, we get a new similarity. Here we can see the similarity in our actual GUI. This similarity is calculated every single time we refresh the screen. So if we have a new product vector embedding or a new search term vector embedding, we can immediately see the difference. In this case, because we obviously have a new search term vector, we need to refresh the screen so it recalculates all of our values and will show the most appropriate search term at the top. So let's quickly look at our actions. So we have the start table task. This is just a dummy task. It is on the filter product table, which is the table where we enter our search term. We then take the two output variables, which are the user ID and the search term. We provide the search term to our LLM embedding connector. Like last time, we are still using the same generative AI provider. Again, we are using a search term as the variable to input to our large language model. We then get back our embedding. We store this in a variable, and we can then store that variable in our database like we did last time. So again, we're updating the filter product table with the user that is currently logged in and its vector embedding that was just generated. Last step that then happens is that we refresh the table. This is just a refresh table task. Again, as mentioned, this is necessary in order for the view to recalculate the similarity. So now that all the logic is implemented, let's take a look at it in action. So I'm going to go back to our universal GUI, and instead of something rich and velvety, I'm going to look for something mystical, a little adventurous today. So let's trigger our search, trigger the process flow we just implemented. And if I scroll back to the top, I will see Mystic Mornings. Experience the enchantment of Mystic Mornings with our premium blend of coffee beans. That sounds just what I need. And we can see that if we look at the similarity. Usually you probably wouldn't show this to an end user, but for demonstrative purposes, I'm showing it here in our card list. We have a similarity value of 0.82 compared to the second best fitting one, which has a similarity of 0.76. So we can see that our Mystic Mornings fits a lot better with the text of our search term than Exotic Roast. Sometimes you do have users that want to filter on something they already know, maybe a specific supplier or a specific country. You can still do this. So here I've added a filter form to start querying the actual structured data. So let's say we want to filter on Angola. We can go to our country of origin, select Angola, and we can only see the products that are from Angola. So the Mystic Mornings and the test product. What this allows you to do is combine the natural search with still some data-driven search using our filter forms, so our country of origin field and our supplier field. This is incredibly useful because you're combining the best of both worlds. You can quickly filter based on stuff you already know, and then you use natural language to describe what you don't quite know yet. So this is our quick look at how to implement natural language search into your Thinkwise application by utilizing large language models and embedding. I hope you enjoyed this quick overview. If you happen to have any questions, you can send them to me via email or ask them in the Thinkwise community. I'm active there. Or if you happen to work with a Thinkwise developer, you can ask them and they can also help you.